morning, guys. Today we are just continuing for the next session, that is of semiconductor diodes and application, session 2 about the diode biasing. Okay, in the previous session we have just studied about the diode. So the diode means the p-n junction formation along with the what are the majority carriers in PFET as well as minority carriers, that is holes and electrons. Okay, in the same pattern for NFET it will be for n junction, it will be electrons are the majority carriers and holes are the minority carriers. So in this session we will just go through your biasing. So what is biasing means? We are just connecting a external voltage source. Okay, biasing is just connecting a external voltage source to make the PN junction active depending upon the direction. So it will be having two types, that is forward biasing as well as reverse biasing. That is, so what is biasing? Biasing is the setting of the initial operating conditions, that is current and voltage. So whether we can apply the current or the voltage of an active device in an amplifier. Okay, next, a bias circuit is the portion of the device circuit which supplies the steady current or the voltage. So the main thing is connecting a PN junction to an external DC voltage source. Depending upon the polarity of the DC voltage externally applied, the diode biasing classified into of two types depending upon the voltage polarity, that is positive to negative or negative to positive. That is for anode or the cathode. We are differentiating into two types, forward biasing as well as reverse biasing. Okay, so this one now we will just go for the diode. What is the diode and what is its symbol and sign? Okay, a PN junction is also called a diode. In the previous session only already know that the combination of PN junction is known as a diode. Diode is an electrical component that allows the flow of current in only one direction. Okay, so this one is very much important. So diode, an electrical component that allows the flow of current in only one direction, whether it might be in a forward bias or in a reverse bias. Okay, so in a circuit diagram, a diode is represented by a triangle with a line across one vertex. Okay, so these are the two things. So this one is the symbol of the thing. Okay, anode as well as the cathode. That is always the anode represents your P junction and the cathode represents your N junction, a triangle drawn with the vertical line. Okay, so this one is the symbolic structure. Okay, the line represents a small part is being represented is known as your cathode part, and the longer part that is represented as a anode part. See here. So this one is a symbolic diagram and this one is a real diode. The mark whatever it is being shown by a line, so that represents a vertical line, so that one is known as your diode. Okay, so this one is the anode part as well as this one is the cathode part. Now the connection will just go through. Okay, so what is this forward biasing? Forward biasing, a PN junction is said to be forward biased when the P type of regions of a junction is connected to the positive terminal of a voltage source and the N type region is connected to the voltage source in the negative terminals here. So if I just consider this as a diode, the positive terminal is connected to a anode and a negative terminal is connected to a cathode. Okay, so this one is the schematic structure of a PN junction. See here, so this one is a P type and this one is your N type, and already we know that in P type holes are the majority carriers and in N type electrons are the majority carriers. In this one electrons are the minority carriers and in this one holes are the minority carriers. Here just the thing. So the positive is being connected, the positive terminal is connected to a P type and a negative terminal is connected to a N type, that one. So this one is a symbolic structure. Okay, so this one, so what will apply when we apply a voltage source? Okay, so this one is just the VI characteristics of a forward bias. Forward bias means always it will be in a positive thing. So this one is the voltage across the current characteristics of a diode. Okay, so this one is the representation, and this one is been considered for the silicon. Okay, so we are just representing a point A, point B as well as the point C, and this one is known as a knee voltage, that is a cutoff voltage, and this one 0.7 volts for silicon is the barrier potential volt. So this one is the standard value of a silicon value as we know in the previous section. Okay, first what will be representing at a point A. So just point A corresponds to a zero bias condition. So this one is the initial condition where the voltage and current will be always 0, and what will the point B represents to the voltage bias less than 0.7 volts. So B means it's going on raising a little bit, and this point is known as your V voltage bias, and it will be always less than the 0.7 volts if you consider for silicon, and if you consider for germanium then it will be of a 0.3 volts. And so yeah, point C. Next, point C corresponds to the forward voltage approximately equals the barrier potential. So 0.7 means it is a standard value, and it is always almost it is same for this point C. That one is the 0.7 volts. Okay, so this one is a straight, means as soon as it reaches the 0.7 it the current increases vertically. Okay, in reality the forward voltage can be such as approximately 1 volt. So this is a 0.7 volt means obviously it will be nearly a 1 volt depending on the forward current, and the forward voltage at which the flow of current during the PN junction begins increasing quickly is known as a knee voltage. So this is the point at which the current starts increasing quickly. So this one is point as a knee voltage, and this one is for silicon it is 0.7 volts. At this point the current starts increasing quickly or sudden rise it will be having. So this one is known as the knee voltage. Okay, this voltage is also known as the cutoff voltage. Cutoff voltage means after this anything voltage has been applied, so it may damage the diode. Okay, so this one is for the both the forward characteristics of germanium and silicon diode, and it is almost the same thing. Okay, instead of 0.7 it will be just the 0.3 for germanium. Remaining all the stuff will be the same. So here the 0.3 will be acting as your cutoff voltage or the knee voltage. So this one is just the thing. So I hope so the figures are been clear here. So this one is characteristics of the silicon diode, and this one is characteristics of a germanium diode. So silicon diode it is of a 0.7, and for germanium it is of a 0.3 volts. Here silicon representation as well as the germanium, the characteristics are being same. See here the length is been reduced. Okay, if the external voltage applied on the diode is less than 0.7 volts in silicon and 0.3 volts in germanium, only a small current flows through the diode. This current is considered as negligible. Means if the external applied is less than the 0.7 means a small flow of current will be there. So at this point only we will be just considering. Okay, remaining bits it has been just been neglected. When the external voltage applied to the diode reaches 0.7 volts for silicon and 0.3 volts for germanium, the diode starts conducting large current. See at this point only the means when there is a sudden increase in the current, at that point only the diode starts conducting, and for germanium it is 0.3. Okay, this current is known as a forward current. The forward voltage at which the diode starts conducting large current is called a knee voltage. Okay, and the cut-in voltage for silicon diode is approximately 0.7. For germanium diode it is 0.3 volts. Next, so here there are some of the diode parameters, that is the okay. So every diode will be having its own detailed information about the diode, and that one is been given in a standard data sheets for every diode. So it means different companies will be having the different data sheets. Okay, in normal terms we will be just representing some of the terms, that is the VF represents your forward voltage drop, that is the small voltage across the conducting diode, and it is called the forward voltage drop, and it is about 0.7 volts for normal diodes which are made up of silicon and 0.34 volts germanium. So that is the knee voltage, whatever we will be telling at the point of knee voltage, that one is known as the forward movements at which point the diode starts conducting. So that one is known as the forward voltage drop, and it is for silicon it is 0.7 and germanium it is 0.3 volts. Okay, and the knee voltage, the forward voltage at which the flow of current during the PN junction begins increasingly quickly is known as the knee voltage. Okay, so this is the point. So sudden start is known as the knee point, and it will be for silicon it is same 0.7, and for germanium it is 0.3 volts. Okay, next IF. So that is the max. So it will be having the two character, maximum as well as minimum. So maximum forward current. So it is the maximum instantaneous forward current that a PN junction can conduct without damaging the junction. If the forward current is more than specified rating, then the junction gets destroyed due to overheating. So it is having, the diode is having its own, that is, if it is increases more than 0.7, then obviously for silicon the diode starts conducting, and as soon as it reaches crosses 0.7, then it might damage the diode. The same passion for 0.3 for germanium. So this one always will be having a maximum forward current. Beyond that, it may damage the diode. Next, RF, that is the static resistance. Static resistance is a forward resistance. Okay, RF means forward resistance, and it is known as the, also known as the static resistance or the DC resistance of the PN junction. When the applied voltage is DC, it is constant resistance of the diode at a particular constant forward current. Static resistance, RF is equal to VF by VIF, or RD is equal to VD by RD. Next, RD means, that is the dynamic resistance. The dynamic resistance is the forward resistance offered by the PN junction under AC condition. That is one of the alternating current conditions. And dynamic resistance also known as the incremental resistance or AC resistance, and it is reciprocal of the forward characteristics beyond the knee voltage. So before the knee voltage, that one is known as a dynamic resistance. Okay, so this one is for the forward biasing. Next, for the reverse biasing. For reverse biasing, the only thing what you are doing is, the external voltage whatever you will be applying, we are just changing the terminal from positive to negative as well as from negative to positive. That is the, now the positive terminal is connected to a N junction and the negative terminal is connected to a P junction. Okay, so this one, see here, the negative terminal is connected to a P junction, PVFET, and positive terminal is connected to a N junctions. Okay, and this one is the flow of the electron flow as well as the hole flow, and this one, the junction whatever is present, the depletion layer is being carried out due to the source, and this one is the barrier voltage, and this one is the barrier voltage whatever we have been just crossing. Okay, next, when the external voltage is applied to a PN junction in such a way that the negative terminal is connected to a P type semiconductor and the positive terminal is connected to a N type semiconductor, holes from the P side are attracted towards the negative terminal, whereas free electrons from the N side are attracted towards the positive terminal, as it is in the same thing as what we are discussing in a forward bias. See, the same thing, whatever the representation schematic, it is being represented in a symbolic form. The cathode part is being connected to a anode, that is the positive terminal, and the anode part is being connected to a negative terminal. Okay, so what is the importance of this reverse biasing? A PN junction diode blocks the electric current in the presence of applied voltage is called the reverse bias PN junction. So it diode blocks the electric current. Okay, so there is also a sudden drop in the reverse bias PN junction. The positive terminal of the battery is connected, the same thing, N type material of the negative terminal of the connected to a P type semiconductor material. The voltage with reverse bias does not cause any appreciable current flow. Means in the reverse bias, normally the diode we can tell it as in a off condition, so there will be no maximum flow of or minimum flow of current. Okay, so for reverse bias also we will be having the diode parameters. Okay, so voltage, breakdown voltage. So normally in reverse bias always it will be having a breakdown voltage. So this one is being represented as a VBR, have a maximum reverse voltage, usually 50 volts or more. Okay, the maximum diodes, whatever the diodes will be having its own data sheets, and if this exceeds, the diode will fail and pass a large current in the reverse correction. This one is called a breakdown voltage or the reverse breakdown voltage. So next one is your IR, that is the reverse saturation current or the reverse current. Okay, so as it is for IF, now it is being represented in IR. Okay, by diffusion magnetic carrier from the neutral region. This is typically 100 nanoamperane for silicon diode. Okay, so this one is VI characteristics of a reverse bias. Okay, so see here, so voltage, reverse voltage as well as the reverse current, that is, so in milliamps as well as in voltage zone. See, this one is the reverse saturation currents, and there will be a sudden flow of things. So this one is known as the breakdown voltage. Okay, so reverse characteristics of a diode. So we'll just go through. The junction resistance is very high, and it is results no current flows through the circuit. See, there is no flow of current. Okay, but in practical, a very small current of order of microampere flows through this circuit. This one is known as a reverse saturation current, IS, and it is due to the minority carriers in the junction. So theoretically we can tell there is no flow of current, but practically when we are doing, we will be having a small current of, there will be a small flow of current. So another thing, there are few free electrons in the p-type and few holes in n-type material. These free electrons in p-type and holes in p-type are called the minority carriers. Okay, so that will be applying in your reverse bias. So reverse bias applied to the p-n junction acts as a forward bias to their minority carriers, and hence small current flows in the reverse direction. Okay, theoretically we will be telling it as there will be no flow of current, but practically there will be a little flow of current. So minimum current or there will be. Okay, next, if the reverse supply is increased continuously, a stage is reached where the breakdown of the junction occurs by a separate increases of the reverse current. This may destroy the junction. If we go on up increasing the reverse voltage, then obviously it will be just damaging the diode. That is the thing. So this one, so both the combination of forward bias as well as reverse bias. So these are the diode characteristics. Okay, see here. So when the positive terminal is connected to anode and negative terminal connected to a cathode, so forward bias will be so. So this one is the VF will be the forward voltage, and it will be for 0.7 volts for silicon and 0.3 volt for germanium. And when it has been changed, then so what it will be having? So they will be having a reverse thing. Okay, so forward biased, reverse biased. Okay, so one thing what you want to remember here in this thing, the whole session is, so diode cannot conduct in a reverse bias condition. So this one is the major factor, or what you should be remembering is diode cannot conduct in reverse bias condition. So there will be no flow of current. Next, diode can conduct only in forward bias condition. Okay, next, so this conductor has a voltage drop of 0.7 volts and germanium has a voltage drop of 0.3 volts in the forward bias, since because in reverse bias condition there will be no flow of current. Okay, now, so where these diodes can be applied, that is the thing. So we can normally these rectifier circuits for AC to DC conversions. Okay, next, over voltage protection circuits. So it can also be implemented on limiter ring, clamping, voltage doubler circuits. Next, signal detector in AM or FM receivers, in transistor bias component networks, as well as digital logic gates and circuits. So in these are the applications of your biasing of the diodes. Okay, so where all means almost in all the components will be just finding your diodes. Okay, thank you. So this completes your second session of your module 1, that is the diode biasing. In the next session we will be just continuing with your Zener diode. Okay, thank you.